markedly in a wide variety of subdisciplines. You're finding that people are reasoning not algebraically, not syntactically, but geometrically, diagrammatically. Now, for me, the pinnacle of these sorts of arguments is this beautiful idea called sphere eversion, and it's encapsulated in this beautiful YouTube video, which is 20 minutes long, so I'm not going to play it, but the first 90 seconds are sort of self-contained and they're really fantastic. Unfortunately, the audio is not working, which is a real shame, because there's a sort of witty bit of banter between a narrator and a sidekick, which I'm going to attempt to replicate. All right. So this was produced a long time ago, right? You can tell. I'm not sure what the date was. In the 90s, I suspect. Hey, I've heard you can turn a sphere inside out. I won't tell you what accent that's supposed to be. But that doesn't make any sense. I can't remember what on earth they say. I wasn't expecting to have to do this. Imagine that your sphere is made out of an elastic material which can bend and stretch. You can bend it and you can stretch it like this, locally, and it can even pass through itself. But you can't bend it infinitely tight or tear it and it will destroy itself. Here we're bending it infinitely tight and it just melts away. Okay, so we can pass it through itself, but we can't bend it infinitely tight or crease or pinch it. So, does that make it easy? Well, let's just try turning the sphere inside out. That's what we're trying to do. So let's pass two parts through each other, but then we get this crease around the equator. So it seems like that's not going to work. So we can try it again. Let's pass it through in a different way. Still, we've pinched to a point at one side, and it gets destroyed. So it seems impossible, right? There doesn't really seem to be any variation on this theme. However we try to pass the sphere through each other, it won't turn inside out. But there is a way to do it. Which looks like this. Okay. So I think that's stunningly beautiful. And it's well known that you can turn a sphere inside out. So if you have a sphere in 3 dimensions, like a beach ball, right? You might have it at the beach. You can't do it because the beach ball can't pass through itself. So what if the beach ball was in 4 dimensions? Well, then the beach ball can pass through itself because it can sort of go into the 4th dimension, and then you get these self-intersections. But the self-intersections can't pass through themselves, and it turns out that you don't have enough space in 4 dimensions to turn the sphere inside out. In 5 dimensions, the self-intersections can pass through themselves, which gives you a bit more space to get some self-intersections, but still the sphere can't turn inside out. In 6 dimensions, you get intersections, the intersections can pass through themselves, and the self-intersections can pass through themselves. And in 6 dimensions, you can turn a sphere inside out. So this, what we just saw, really happened in 6 dimensions. So it's a fantastically complicated geometrical proof. And imagine you're a mathematician, you've been working on this sort of problem, and you know, you have a particularly long bath, and you think, I've cracked it, I've done it, I've worked out a much more efficient way to do this. How are you supposed to convince your fellow mathematicians, right? What are you supposed to do? Make a movie? Okay, you need a production budget and, you know, editorial assistants and, you know, 2 years and some skilled graphics designers. This isn't a suitable way to communicate these sorts of geometrical ideas. What if you made a mistake, right? I mean, the pixels, you can't tell it from the pixels of the video, right? Maybe this is garbage. Maybe it's just a pretty picture. Maybe you can't really turn a sphere inside out after all, and it was just sophistry. So we've got a problem, right? The problem is that these sorts of techniques are being used all over the place now, but we don't have any real formal sense of what they are, or what they mean, or how we can handle them. One of the ways that I got interested in what people are doing here with Roland is a talk that Greg Meredith gave at Ether DevCon 3, which I think was last year, and he presented some contracts, and he explained about how it's some Roland contracts, and he showed how you can represent those contracts geometrically. Just glance at the contract, you don't get much insight, but glance at the graphical representation, and with a little bit of practice, you can immediately see what's going on. And you can see by eye where the non-determinism might be, where the bottlenecks might be, and so on. So this is an idea that's really permeating and becoming increasingly dominant throughout mathematics and computer science, but also in particular might, I think, be extremely useful as a way, if it matures, to visualize, work with, code, reason about, manipulate Roland contracts in the fullness of time. So where can we trace this back to? We can trace this back to Roger Penrose in 1971. Roger Penrose is a very famous mathematical physicist, worked a lot with Stephen Hawking, worked a lot on gravity, and he noticed that, I imagine lots of people here have a background in physics or mathematics. You might have seen expressions like this: theta, d, b, c, psi, d, b, a, c. Whenever you have a repeated index, that means you're supposed to sum. But he said, instead of writing these symbolic equations like this, why not draw pictures and have a blob with wires coming in for a tensor? So here, theta has got three indices, b, c, and d. So here it's represented by an object, a circle with three wires. There's one wire, there's one index. And if you want to have two indices in common, so here there's a d index on the theta and a d index on the psi, then you run a wire, that wire that's labeled d, from the circle representing theta to the triangle representing psi. And then the great thing is, once you've done that, you don't need to label it d anymore. You can take the label off. That was a bound variable. That variable was just existing to say, this variable, which is being produced by theta, is being consumed by psi. But you don't need to know that it's called d, and of course up to equivalence you could have called it, up to alpha equivalence you could have called it anything else. So the geometrical representation is in some sense more natural because you don't have to give this redundant information. But 5 decades later, and despite this work and some other impressive and important work, when you go beyond the very simplest diagrams, say when you go beyond planar diagrams and consider three-dimensional diagrams and so on, there's very little that we know. What is the formal status of these diagrams? How can we create them, share them with other practitioners, with people who want to use them for whatever reason? How can we use computers to help us do this? Because of course it's insane to imagine that for these complex sorts of graphical representations, we'd be creating them by hand in our notebook, taking pictures of them, right? This is not a way we're going to be able to adequately handle the complexity of these things. So let's step back a bit and think about some broader ideas in computer science and mathematics. So one of the most important links between these subjects comes from the Carey-Howard correspondence, which I know a lot of people here will know about. It's a very famous idea. It says that if you've got a proof of a certain sort, in particular a proof which is constructive, so if you're using excluded middle and arguments like this, then this doesn't go through. But if you've got a proof that's constructive, that's of a certain nice kind, then from it you can produce a program. So you can then run, you can run the program, so you can run your proof. And what that does is, what's the input of that program? Well, the input of the program is the hypotheses of your proof. And the output of your program is something that has the type of the statement of your proof, the overall theorem that you're proving. So proofs turn into programs that take hypotheses into the result. And in some settings, like a sort of functional programming setting, this dichotomy is so well understood as to be even invisible, right? And you would write a program and think of it as a proof at the same time. I would argue that there's something missing here. What is missing is geometry. Because while you can take a proof and think of it as a program and run it, I would say you can also think of it as a geometry and visualize it. And just as when we think of a proof as a program, we gain a completely new perspective on the mathematics we're trying to do, because we start to ask questions like, when we think of a proof as a program, we start to ask questions like, can we run it? Will it halt? Okay. Is this similar to the sort of things I've produced in other programming languages? You wouldn't think about asking those questions just if you stayed in the mathematical world of proofs. Similarly, if you can take your proof and visualize it as a geometry, you can start to ask completely new types of questions that you would not have thought, would not have occurred to you to have asked before. Can I look at this in a different way? Can I perform an isotopy? Can I spin it around? Can I turn it upside down? Can I make a model of it? Can I 3D print it? Okay. What's the volume of my proof? What's the surface area of my proof? Gives you a completely different suite of ideas, of inspiration. Gives you a completely different way to look at what you're doing. And of course, the idea is that this triangle has no node privileged, and that in principle one ought to be able to move around this triangle and explore it in its fullness. Now, this is not supposed to be easy. I don't claim for a moment that any proof you give me, I can give you some geometrical representative or vice versa or anything like that. This is a vision I have that's driving a lot of my work. And in some special cases, you know, it works out. In a lot of cases, I don't know how to make it work out yet. But, you know, that's why they call it research. So proofs and programs, therefore, I claim have an innate geometrical essence. And viewed in this way, we can obtain new perspective and insight. And my long-term goal then is to make this insight relevant and useful for real-world programming languages, maybe for something like Golang. So let's make this really, really concrete. Here's a simple example from group theory. So if you've studied any mathematics, probably any physics, maybe any computer science, you'll know what a group is. It doesn't matter if you don't know what a group is, because this is such a simple example, it won't even matter. So in a group, you've got some elements, and you can multiply those elements together to get other elements. That's the idea. So suppose we've got a group with elements L, X, and R, satisfying some equations. Lx is E, L times X equals E. E is a special element called the identity of the group. And if you multiply with E, nothing happens. So if we're thinking about a group of rotations, then E might be like rotate by 0 degrees. So it's a perfectly good element of the group, but it doesn't do anything. So L times X is E, and X times R is E. So maybe we've got 3 elements, L, X, R of our group, with these properties. Then we can prove that R equals L. And we can prove it like this. So we start with R, and we say, well, that's the same as E times R, because E doesn't do anything. But E is L times X. So that's the same as L times X times R. But this is something I should have said earlier. Groups are associative as well. So if we've got 3 things we're going to multiply together, in this case L, X, and R, it doesn't matter whether we multiply L by X and then by R, or if we multiply L with the result of multiplying X times R. So that rule is called associativity, and in a very wide range of settings, that's something that you want very often. So a group has to be associative, so we can use the associative rule there. And then we say, well, XR equals E, so we get LE, but L times E is just L, because E doesn't do anything. Okay, so that's a very simple proof in group theory, that in this setting, R will equal L. Now we can look at this, this data that we've drawn on the page, and we can think, is there any other way to understand or to represent what we've done there? And what we might do is we might say, well, look at L. Look how L is appearing on every line here, like this. And look how X is appearing on every line here, and R, similarly. So it might occur to us to draw some lines over our proof, like this. This is black, we can say black means L, red means X, yellow means R. little bit of patriotism there, German flag colour. And maybe if we're doing these calculations a lot, we might get so used to thinking of things in this way, after a while we might realise that we don't need to write down the symbols at all. As long as we are aware of what the rules of the game are, and we know what we're allowed to do with these coloured strands, we can realise we can prove a lot of things in group theory just by drawing pictures like this, pictures of pieces of bent wire. Now, that's absolutely the case, and people do use this sort of notation a lot to reason in groups. But something sort of amazing has happened. This syntax that we've developed of coloured strands is really objectively simpler than the syntax we started with. So we've got 3 colours of strand here representing L and X and R. What about this element E? E we had to care about before, we had to write it down. E was the thing that didn't do anything. But now, if you look where the E went, the E is just nothing. We don't draw anything for E. E doesn't do anything, so why do we need to draw anything? Also, what about this associativity mumbo-jumbo that wasted our time in the middle of the proof? Nothing happens with the strands there anymore. So we can forget about associativity, we can forget about units. And the proof theory, in terms of the diagrams, is not only equivalent in the sense that everything you can prove using these strands, you can prove using the traditional syntax and vice versa. I mean, it's really simpler. We've thrown away some of the structure of the theory of groups, which seemed important, but turned out not to be that important after all. So this is a small example, but I think it represents very well the way in which and the reasons why these sorts of geometric representations arise very naturally in very general settings, even in a setting like group theory, which seems as far from geometry. Well, group theory is very close to geometry, but everything's close to geometry, really. But you're a freshman mathematician, you're taking your group theory class, you don't expect you're going to be drawing pictures, right? But you may as well be. Okay. So now let's talk a little bit more about category theory. Because that's the branch of mathematics that's underlying everything that's happening here.
So,
yeah. No, we're not going. We're barreling on.
What was trying to be proved?
Well, we proved that black equals yellow. That's what we proved here. We proved that black equals yellow. Okay. So what is a category? Well, I'll tell you what a category is. It's a very simple thing. It's an abstract mathematical entity. It's got objects. We can call them whatever we like, but we'll use capital letters A, B, C, D. It could have finitely many objects, it could have infinitely many objects, it could have a class of objects. It's also got morphisms. Morphisms are like arrows. They start somewhere and they finish somewhere. So here, F, G, and H are arrows. F goes from A to B, G goes from B to C, H goes from C to D. We could have lots of arrows going from A to B, or we could have no arrows going from A to B. Right? We've got, all we know is we've got some objects and we've got some morphisms, and every morphism has got some source and some target. Morphisms can be composed because the idea of a morphism is that it's a way to get from some place to some other place. So if F gets you from A to B and G gets you from B to C, well then you can get from A to C. So there has to be a morphism from A to C. And that's the composite of F and G. And if we're talking about getting places, well, so we can also compose G and H. And then again we have this associativity law. If we want to get from A to B to C to G, following F and G and H, it shouldn't matter the order in which we compose those together. So if we go first from A to C to make FG, my laser pointer stopped working unfortunately, and then we compose that with H, we get FG composed with H along the top. Or if we compose the other way, we do F composed with G and H. And there's an axiom that says these should be the same. So F dot G dot H equals F dot G dot H. Okay, so what else? Well, if we're talking about going places, a way that you can go somewhere is just to go nowhere at all. And in a category, you have to be allowed to go nowhere at all, so there are these identity morphisms that go from every object to themselves. And if you compose with these identity morphisms, nothing happens. So if you start at A, you do the identity morphism on A, and then you do F, it's just the same as doing F. And that's it. That's the definition of a category. Very, very, very simple idea, but an extremely profound idea, and an idea which is spreading its tendrils into enormous parts of modern mathematics, computer science, and increasingly physics. Examples of categories come from almost every area of mathematical science. So let's just come up with three. A mathematics example might be formulas and proofs. So your objects are your formulas. A, B, C, D are formulas, and F, G, H might be proofs. So F from A to B would mean that F is a proof that given A, then you can conclude B, for example. A computer science example is types and programs. So A might be a type, B might be a type, and F is a pure program which takes in inputs of type A and produces an output of type B. A physics example might be systems and processes, thermodynamic systems, quantum systems, classical systems, all sorts of systems. Because what's happening in all these cases is we've got stuff happens to stuff in an associative way. And this basically unifies all of modern science. Okay? But that's what a category is. That's just as much and as little as a category is. So for this reason, category theory is everywhere. And by the way, the Carey-Howard correspondence says furthermore that these categories often are just going to be the same as each other. Right? So the Carey-Howard correspondence then gains real concrete mathematical meaning. Because you can build this category from formulas and proofs, build this other category from types of programs, and they'll just be the same category. And the language, the abstract language of category theory, lets you say that in a non-trivial way. So, what then is categorification? Categorification is like category theory, but even more category theory than category theory. Okay? So, we've got objects, we've got morphisms. But now we've got two morphisms which go between the morphisms. Because we say, well, maybe F goes from A to B, like maybe F is a program that takes in input of type A and output of type B. Maybe F prime is another program that takes in input of type A and output of type B. But maybe mu is some process that transforms the program F into the program F prime. For example, maybe F uses some dummy variables, and F prime just renames the dummy variables. Then there's a natural sense in which F and F prime are equivalent, and we can use this structure to encode that. But now what happens is something exciting. We have two dimensions of composition now. We aren't just composing F, G, H, L, line. We can compose horizontally or vertically. So we've gained a sort of two-dimensional essence. So in this case, for example, mu and sigma and tau are two morphisms, and we've composed them into a big composite two-morphism whose source is the thing all along the top, F, composed with K, and whose target is the all along the bottom, J, composed with H. And an important example is propositions, proofs, and equivalences. So a structure like this is nice if you want to say, well, I've got a proof that A implies B, you've got a proof that A implies B. These aren't literally identical proofs, but maybe they are morally the same, or maybe they're not. Maybe they are fundamentally different ways of showing this. But then, of course, this can iterate forever, because let's say our proofs are the same. Let's say I've got some way of showing that our proofs are the same. Say you've got some way of showing that our proofs are the same. Well, are our ways of showing that our proofs are the same? Or are our ways of showing that the proofs are the same, not the same? Okay? So this goes on forever. But this is all interesting. This is all relevant, right? If I've got a contract and you've got a contract, maybe I want to check that our contracts are the same. Maybe they're not the same for trivial reasons because we use different variables. We don't care about that. Maybe I can show they're the same. Maybe you've also shown they're the same. Maybe we need to check that we agree the way in which they're the same, so that when we map my data onto your data, no problems arise. These are things that are really at the heart of what we need to be able to, at the heart of our discourse when we're doing fundamental logical methods in computer science, and this sort of categorical language lets us do it. It gives us the setting in which to have these conversations.
Excuse me?
Yeah.
What's the source of tau? Because I assume it ends up.
Yeah, good question. So the source of tau sort of lives in this whole area here. So the source of tau is f prime composed with g. Okay? Good question. So, we're led in this way into the field which is called higher category theory. Okay? Higher category theory, this is a serious branch of mathematics, right? If you're some sort of young genius and you've got your PhD by the age of 6, you know, saying, what am I going to do? Well, you go into higher category theory because there's a lot of very, very profound, hard conjectures out there. And one of the greatest stars of the field is Jacob Lurie. This is a quote, Jacob Lurie's, that there is a general algebraic theory of n categories, but it is generally regarded as a technical and forbidding subject. Now, I think that is a real and profound shame, because this theory of high categories, all it's doing, all it exists to do, is let us talk about situations where we've got some stuff that lives in n dimensions, let's say n greater than 1, and lets us compose that stuff in n dimensions and reason about it. It's a very simple idea, ultimately. And it's what we need in order to make sense of those things we had right at the beginning of the talk. All these different imagery, all these different geometrical methods that people are using in different areas of mathematics and computer science. We need an easy, straightforward theory of higher categories to make sense of these images. So it's a shame that even someone like Jacob Lurie thinks it's difficult. Okay. So let's see why this might be the case. Well, we can look at the axioms that define these theories. And even in their simplest form, a two-category, a setting where you can compose things in 2 dimensions, comprises 3 sets, 6 functions, 12 axioms. 3-category, 4 sets, 19 functions, 58 axioms. 4-category, 5 sets, 34 functions, 180 axioms. So that tells you, if you're trying to reason about something in 4 dimensions, it's going to get complicated. Okay? These axioms aren't pleasant. The whole system is extremely complex. Why is that complexity coming from? Well, because 4-dimensional space is complicated, right? There's lots of ways that you could interact with other objects in 4 dimensions, lots of ways that you could move around. So what would we do with these axiomatizations? Well, we could work in a proof assistant, right, or a traditional programming language, and we could try and let that proof assistant help us deal with this complexity. But that's the wrong approach. It will never succeed, because this setup is too complicated for us to see what's going on. And whatever code we write here, we won't be able to perceive what it's doing. We started with this motivation of these beautiful diagrams, this imagery that people are creating across mathematics and computer science to do all sorts of different things. And this sort of idea moves in completely the wrong direction, okay? Because it says, well, yes, you're composing things in higher dimensions, I know how to do that, it's only 118 axioms. Here's where's your proof assistant, let's get started, okay? That's not going to be an effective way to capture the spirit and the intention of these geometrical notations. Don't get me wrong, lots of people do this and they achieve fantastic things, but I think for some purposes it's not sufficient. So let's think about the relationships between these pictures that we've just seen, these formal pictures that arise in the pure study of higher categories, and these sorts of diagrams. What's the relationship between these things? So here's a diagram in a 2-category traditional sort that we've just sort of seen. So we've got these objects, A, B, C, D. We've got some 1 morphisms, and we've got some 2 morphisms here called S and T. corresponds to a diagram by dualization. Very beautiful idea. So I'm going to flip back between the algebraic diagram and the geometrical diagram. I'm going to try and understand what's going on. So here we've got 6 objects, A, B, C, D, E. They're kind of like points here. In the dual diagram, they're not 0-dimensional anymore, they're 2-dimensional. They turn into these 6 colored regions. So something 0-dimensional became 2-dimensional. Here we've got some one-morphisms, these single shafted arrows. They're 1-dimensional and they're sort of going horizontally. In the dual diagram, they're still 1-dimensional, but they're sort of going vertically now. They've been replaced by wires going in a perpendicular fashion. And what about S and T? Well, here, T, for example, lives in this whole region in between these 4 wires. It's sort of dispersed and diffuse in this whole 2-dimensional region. But in this dual picture, it's been concentrated at this point. T is happening here. So 0-dimensional things become 2-dimensional, 1-dimensional things stay 1-dimensional, 2-dimensional things become 0-dimensional. It's the same diagram in some sense, but we've turned it inside out. Well, not like a sphere, but we've somehow changed the way that we've kept the same elements, we've kept them at the same point on the page, but we're representing it in a new way. Just like what we did with that simple example about doing a calculation in a group. And I think the result is much more readable and much more captivating than the original diagram. So by a process like this, we expect n-dimensional categories to have an n-dimensional graphical calculus. But that's potentially got huge advantages, because it means that instead of worrying about the axiomatic definition of any category, which involves hundreds of axioms, we can instead potentially work with these n-dimensional geometrical objects, represent them with simplices or something like that, and understand and work with them visually by direct manipulation, rather than typing into our proof assistant directly using the axioms of n categories. And this is the first indication, which is very well known, of a duality between category theory, algebra, proof theory, and geometry. So it's a hint to one of those edges in that extended correspondence that I was talking about before. Okay, so what do we do in our work? This is an academic track, I'm afraid, and academics like talking about themselves. So what's our contribution in this area? So what we've done is we've built simple combinatorial models for these higher categorical objects that lets computers understand, work with, and manipulate them. So suddenly, instead of having to work with these very complicated axiom schemes, you just produce these geometrical objects, these pictures, and you visualize them, represent them, manipulate them directly. That's the idea. So we have to do a bunch of stuff. I mean, there's mathematical foundations here. There's questions of encoding, right, and efficiency, because we need the computer to be able to work efficiently with these geometrical objects. We need to be able to visualize and render. So there's a lot of work in UI and front end and graphics. And also then manipulation. You've produced these geometrical objects which are representing your proofs. But then what if you want to change your proof? What if you want to manipulate your proof? It's no good just seeing this geometry in front of you. You want to reach out and change it. Move this bit down, move this bit up. And that's exactly the idea. So that's led to the tool we produced. Version 1 was released almost 3 years ago now. Version 2, we're working on version 2 very intensively at the moment. So this has got good, bad, and ugly aspects. So our tool is based in the browser. Almost nobody does this. Okay? Browsers are very fast. You can do parallel computation. There's no barrier to entry. You don't have, if you've got a prototype system, why not put it in the browser? Okay, it means you won't be able to use a lot of tools that you like using, but it means that if people want to try out your system, they can just click and they're there. They haven't got to download something, update their kernel, compile something else, install 27,000 dependencies, find out that they're on the wrong operating system, right? You lose, I guarantee that you lose 99%, at least of potential casual users of any system by having it in 2018 as something you can download and install. Now, who cares about the casual users? Well, it's the casual users who turn into the serious users, right? So I think you need to care about the casual users. We've had 20,000 page loads in 2.5 years, which for an academic research tool is pretty good. We've discovered new theorems using this system. Bad. So what this system does, and I'm going to demo it in a minute to finish off the presentation. You're working with these high-dimensional geometries. They can be hard to understand. So it's like you're living in some sort of hyperspace, right? We haven't set this up yet, but I've got grant funding for a virtual reality headset, and I want to be able to dive through the hyperspace of my proof and see things in high dimensions. I haven't done that sort of thing yet, but that's going to be necessary at some point. And this system isn't really very intelligent. You can't say, hey, take this geometry and compress it, or expand it, or do something clever. You've got to do everything yourself. It doesn't do anything high level for you quite yet. And the ugly is all written in JavaScript directly. So that's not ideal, but actually, you know, there were some advantages for us working with JavaScript initially. Everything was very rapid. We weren't slowed down by complex sort of build pathways and stuff like that. If there was a bug, it was very, very clear what was causing the bug. And you know, when we started, I mean, we thought we knew what we were doing, but really we had no idea what we were doing when we started. So any decisions we would have made initially about the typing structure, the classes, and so on, by the end, they would have changed 10 times around. So it was nice to have that flexibility and stay near the bare metal. In our next version now, we have more of a clue of what we're doing, you know, the advantages of types, so on, like formal verification, perhaps. Maybe we'll have some access to those. Okay, so now I'm going to give you guys a demo of our tool. So I've got about 12 minutes. So our tool runs at one of these stupid new top-level domains, logger.science. And it turns out that these new top-level domains, .science, .guru, .space, they're basically blocked almost everywhere because it's assumed that it's just some spam site. So for your next tool, I suggest you just use like .net or something. Anyway. So our tool runs at globular.science. So let's see what's going on here. And we're going to prove something using this tool. So we start off, and all we have is the point. There it is. It's a zero cell. That means it's a zero-dimensional thing. It's called cell 1 at the moment. Let's call it A. So I can edit this. I can click on it, and I sort of bring it up large in the main screen. So we've created a zero-dimensional universe here, just inhabited by our type A. Nothing more, nothing less. Okay, there's not much we can do with just A, so I'm going to create a new zero cell, which is B. Well, so what could I do with... okay, so now we've got A and we've got B. These are two isolated points. They don't talk to each other. What I'm going to create is a process that turns A into B. So it's like a morphism in a category that goes from the object A to the object B. So I'm going to click on A, click source, and click on B, click target. So now it's produced something, a one cell, a one-dimensional entity. I'm going to call this F. I'll click on it, and now it comes up large here. Let's use my mouse cursor to investigate this object. Over here we see we've got a line, and every point on that line is labeled A. So this line is formed from lots of points. Every point is A. And then F happens, and now we've got B, 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 B. So F exists to turn an A and a B, so you could into a B. So you could be an A, you could be just minding your own business, hanging around over time, and then suddenly, bam, F happens, and now you're B. That's what F is. That's all that F exists to do. tick a little box here, invertible. What invertible means, that if we think of our process F, think of our one cell F as a process, it means we're now allowed to do our process in reverse as well. So let's see what that means. Well, if I click here, I'll now be able to attach. I move my mouse cursor, I can see what it is, F inverse. So that makes sense. If F turns A into B, F inverse turns B back into A again. So I can click, and I can keep attaching F's and F inverses, making them chain like this. Now this is one-dimensional, so now let's go two-dimensional. To go two-dimensional, we want to stretch this out vertically, right? We want to stretch it up. Mathematically, we want to take the product with a finite interval so that this line is extruded up into a square, into a rectangle rather. So to do that, we click this identity button. So we've taken that and we've now stretched it up, and now it's a two-dimensional thing, albeit something where nothing very interesting is happening in that second direction. But now we can continue to click and interact with this two-dimensional configuration, and we can make some much more interesting patterns. So I'm going to click and drag, I'm going to click, I'm going to click and drag, I'm going to click. So let's see what we've produced here. So at the bottom here, we had an F coming in and an F inverse. Now, what's this move here? F cancel. So the system knew that here I had an F and an F inverse. Well, if you're going to do a process F, but then immediately do the reverse of that process F, you may as well have done nothing at all. And F cancel is the thing that knows about that. F cancel is the thing that lets you say, well, if you're going to do F and then the opposite of F, you may as well just do nothing at all and just have B the whole time. That's what this blue C is. Right? Similar, and all these vertices are similar. So here, for example, this is the opposite. Sorry, just have the C of A here. So here we've just got A, we're just hanging around, we've got two-dimensional area just filled with A. We can suddenly say within our C of A, hey, I just want to pop into B for a bit, right? It's F, so I'm going to use F to take me into B and then quickly back out again. And it's this F insert cell that will do that. So we can click and we can produce some configurations. So this is two-dimensional. But the whole point of high category theory isn't just that you want to, and the richness of this subject isn't just that you want to be able to compose things in two dimensions. It's that you want to be able to isotope and move those things around in their ambient space. That's the critical, non-trivial part of the game. And we do that in this system by direct manipulation. So I can move my mouse cursor up here, I can click and drag down, it will move down. I can click and drag down, down. Sometimes there's more than one possibility, and I have to choose what I can do. And in this way, I can morph what I'm producing. I can move these things around, a bit like cells, a little bit like biological cells, these things. And you can change your 2D configuration however you like. So this system has got an enormous amount of freedom. You can define any sorts of points that you like, any sorts of one-dimensional things, any sorts of two-dimensional things. So I'm just going to do this a little bit. I'm just going to do this a little bit more. So we go up here, we go up here, up here, up here, maybe down here again, down here, up here. Depending on the way that I click and drag, I can cause things to move around each other. So this guy here is on the right of this little finger. I move him down, and then move him up and drag him to the left. I can get him to move up and drag him in different ways. I can get him to move around on different sides, like that. Okay, so over time we build up a big history of what we're doing. But if you've noticed in the corner, this little slice counter has been building up. So we're tracking what we're doing. So it says 19, we've had 19 steps, and I can roll back, and I can roll forward and look through the slices. If this was a mathematical proof that we were building, then we might look back over the proof and say, oh yeah, I could have done that in a simple way. So we could just delete everything, start again. But using this system, we can do something better. What we've produced here is a sequence of two-dimensional images. It's a bit like a CAT scan, right? If you go to the hospital, you get a CAT scan, you get a sequence of images, which, you know, there's a huge number of these images. Altogether, it tells you pretty much everything you might want to know about what's going on inside you. But, you know, if you sign up for a dating site and say, hey, send us a photo, you don't send your CAT scan. Okay? You send a different sort of photo. You send just one photograph. Even though you're a three-dimensional entity, you send just one photograph, sort of taken from the outside. So that doesn't show all the information about you, but it summarizes you in a single two-dimensional image, which loses some information, but it's good as a summary. So the situation here is very similar. We've got all these two-dimensional slices. We can scroll forwards and backwards through these two-dimensional slices and get a complete, perfect picture of the proof that we're developing. But we might say, hang on, I can't see the wood for the trees. I can't see the forest for the trees. I just want one image where I imagine stacking all these 2D slices on top of each other to make a single 3D thing and look from the side. And actually, this system, you might imagine that it's storing these two-dimensional images slice by slice, but it isn't. It's storing just a single three-dimensional object. And as we're going through it, it's creating the CAT scans. But we can ask it, just show me this three-dimensional image from the side. And that's what this project button does. So we click project, and now we see this. Wow, we see something that looks completely different. So let's zoom in to this three-dimensional object and look around. It looks like a knot. We've got these braids and these links. So we're uncovering a profound relationship between proofs and knot theory. Basically, whenever one thing moved in front of another thing, shows up here as a little knot. But then looking at our knot, we can imagine that this is made of pieces of string. We can say, well, we can simplify this knot, right? Because here, I move this over, and then I moved it. Well, what was the point? That didn't achieve anything. Maybe I was confused. Maybe I didn't know the most efficient way to build my proof. So I thought that would be a good thing to do, but then I changed my mind and I moved it back. So here, looking at the 3D geometry, we can go in directly and we can simplify it. It's as if we're just sticking our hand in and we're teasing up and we're teasing these strands apart, simplifying the configuration. We can do this here. We click and drag. We've simplified that, smoothed that part of the knot. And in this way, we can look at what we've done. So yeah, I'll simplify that. And we can change the configuration and simplify the proof that we're doing. And then we can unproject and look through at our simplified object. Now we need 15 slices. It was 19 before, because we made some simplification. So that's the end of the demo. So let me summarize the point about this sort of mathematics. We've got proofs and we've got programs, and these are two very different perspectives, and very important perspectives. But that misses something, I believe. It misses geometry. It's not clear how we can do this for all programs by any means, but for some proofs, for some programs, they have a geometrical equivalent. We saw that, for example, in this case of group theory. And if we take that seriously, we can use that directly as a new sort of computational paradigm. Instead of building a proof or writing a program, we're drawing a picture, literally. We can visualize that picture in new sorts of ways. We can understand things about it intuitively that we would never have managed to understand by looking at the source code, say, written in some more traditional language. This perspective isn't better than any of those other perspectives. It's complementary. It's a different view. And by moving around between these different perspectives, I think in the future, I hope that that's how a lot of computer science and mathematics will be done. And I think that it's something that, you know, within the next 2, 3 or 4 years could be a really useful tool for something like ROLAG that really seems well suited, I think, to this sort of representation. Okay, that's the end of my talk. Thanks. So I guess no one's in charge, so any questions? Yeah.
Would it be practical to prove, say, the monad laws using this approach?
Oh yeah, that's just perfectly suited.
And how would that proof look like?
Well, when you say prove the monad laws, you mean from something, right? So you would want to prove that given blah, 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 then prove that it's a monad. Right? And depending on the nature, there are many such blah, blah, blah where this tool would be perfectly suited. Maybe there's some other blah, blah, blah where it wouldn't be suited. But yeah, monads are the sorts of things, monads are a great example because monads are things that are really important to functional programming, but they also have an extremely natural and profound geometrical representation. And often if you look on the online literature about monads, you'll see that theorems are proved about monads using pictures, because it's just the most direct and easy way to understand what the monad is doing. Relationship between the multiplication and the unit. These things. Yeah.
So, if suppose you find some way to geometrically realize, any program or proof or something like that, and of course we could move in. These probably just wouldn't be two-dimensional, but could be n-dimensional. My first instinct is to say that we have so many algebraic tools. We can calculate homotopy groups, homology groups. Have algebraic tools on geometry like manifest themselves so far in your work in any useful way?
So there are a lot of existing computer programs to help people work with geometry, absolutely. I don't think there are any that works in this sort of way. I think they're filling a big gap. But nonetheless, those other tools are doing lots of important things. They're computing invariants of your spaces, they're looking at your homology, cohomology, whatever it is. And it would be great if this system could interface with those other sorts of systems. I don't even know the first thing about how to do that because there's 1,000 different things we want to do with this system. But it sounds like a great PhD project. Yeah.
So for me, you can prove pretty easily that it's a fun. Like with equation, just a few lines. Do you think we could do that with images like now?
So what do you mean?
Like, so to prove that maybe it's a fun.
Oh, I see.
Yeah. That's basically what he said, but simplified.
I see.
Just the fun.
Okay, so you're asking about some specific thing, and I have to say I wouldn't know. Oh, yes. Yes. Oh, great. But
no, my question was, could you show us now? Because if you were to show us with diagrams and with the equations, it would be like really easy to show. But I was really curious how it would look with these diagrams.
yeah, I don't know, but it sounds like Aaron knows. So let's chat about it in the break. Oh, he's done it already.
I show you.
Yeah. Let's talk about that later. Mike.
So, much of the work that we've been working on for Ladle uses graph-enriched categories. These categories are also have finite products, so I guess you could say that there are roughly 3 categories. If you treat product as an analytical operation, object 3 categories. Would it be feasible to reason about these theories in Globula?
So I sketch a ground idea of an equivalence between proofs, programs, and geometry. So in a program, the most basic sort of data type constructor is the pair. Okay? If I've got data type A and data type B, then I can build a new data type A times B. Okay? So you have a function that doesn't just take an A, or just takes a function that takes an A and a B. And that already defeats my triangle. Okay? Already for something like that, I don't know what the geometrical analog is of products in that way. But I've got what I think are some really cool ideas, and that's probably for me the major that for me is the most exciting near-term thing to do. To build products into the system, so that a system like this isn't just working with infinity categories, but infinity categories with products. That for me is the next major goals. Which conveniently is exactly what you need. Any other questions? We're going over into the break. I'm happy to answer any more questions